So this room will be about atomic structure and mass spectroscopy. This is kind of an essential concept of chem. Mass spectroscopy, that's a big word. It's a little less important than atomic structure is, but I think it's really revealing knowing about it. The questions that are asked as a result of mass spectroscopy, like the data you get from doing that experiment, you'll be asked a lot about, but in terms of the actual experimental procedure, you shouldn't have to know too much about it, so don't worry about it if you don't get it. Follow Fivel on social media, Instagram, Twitter, YouTube. I don't really use Twitter that much, and my YouTube is more for less nerdy stuff, so I don't really follow. I follow on Instagram. One thing that is really great from following Fivel on social media is Fivel will send out emails to members, I think, or I'm almost sure they'll send out emails to members about streams that are coming up, but who checks their email, right? Just kidding. We should all be checking our emails. But we're all teens. We're all checking our Instagram. So it's a lot better. Also, I'm a little sick, so if I'm coughy or nasally, I can't do anything about it. But yeah. So we're going to be talking about Dalton's atomic theory, why it's important to modern science, subatomic particles, Coulomb's law, and isotopes, hyphen notation and nuclides, mass number, average atomic mass, what a mass spectrometer is, and what you do with the data from the instrument. So first is Dalton's atomic theory, and Dalton's atomic theory is that all matter is made of discrete building blocks called atoms, and atoms are indivisible and indestructible. So if you think of you have a Lego tower, well, I gotta be careful saying Lego, that's a copyrighted thing. If you have a toy brick tower and you stack it on top of each other, if you stack enough of them up, you're not gonna be able to see the individual bricks, right? But you'll be able to deconstruct it, but unless you're some superhuman that can rip Lego bricks apart, you're not going to be able to divide it further than the Lego bricks. And that's essentially what this says, is that all matter is made up of these little discrete building blocks. What do you mean by that? I'm curious. Because I mean, in the sense of dark matter, yeah. Well, yeah, a proton is a part of an atom. Okay, yeah, I guess in that sense you're right. It can be split up using nuclear nuclear reactors and all that good stuff. So yeah, strictly speaking, this isn't right, but it's a good starting point. And another part of the theory is that all atoms of a given element are identical in mass and properties. So for example, if I have an aluminum atom here, they're going to have the same number of protons, and if they're the same isotope, which I'll define later, then they have the same mass, and the individual building blocks inside that aluminum atom have identical mass. And compounds are formed by different atoms or different types of atoms. And essentially, I was going to put a water graphic in here, but I messed up. But if we have H2O, for example, if it looks like this, there's hydrogens on each end of my finger. There's an oxygen in the middle. So essentially, these compounds are formed up by elements that are bonded together. I'm sure everyone has at least a surface level knowledge of that. And it essentially says every compound is formed up of these elements, of these fundamental elements. And you'll get those from your periodic table, and you'll get that on the AP exam. And then a chemical reaction is nothing more than a rearrangement of atoms. So proportions. Well, if you look at in terms of proportions, right? If you break it down to the most fundamental level, proportion doesn't matter, because a portion will be for example, grams per mole, right? If you break it down together, then those will have the same mass, identical to another element or another separate thing. So a chemical reaction is nothing more than a rearrangement of atoms. So for example, a chemical reaction would be the dissolution of water. You have water right here, and the dissolution says the one hydrogen is pulled away, and you're left with an OH and an H. So that's essentially what that is, and the atoms are rearranged. And its importance to modern science, and I'm sure all of you guys briefly know about atomic theory, so I didn't really spend too much time on it, because it's really if you're taking AP Chem, you should probably know it, because you probably learned it in middle school, or at least I hope you learned it in middle school. If you didn't, There's more simple things, but this is an AP lecture, and I don't want to really waste my time on something that's not that important. So the first thing that's important to modern science is an emission spectrum for any element. And this is the emission spectrum for hydrogen. And what the emission spectrum essentially says is you take an atom and you excite it, you give it energy, and when it excites, it vibrates. And when it vibrates, it'll lose a lot of its electrons. And when it loses an electron, well, it doesn't really lose it in a strict sense. The electron goes from one energy level to another, further away from the nucleus, and that will release light. And you can look at these emission spectrums that are unique to every element, and you can see what kind of light is released from an electron jumping from someplace to another place. And then you can also tell where that is. You can tell how much energy that electron had to do to move, because the color corresponds to how much energy was in that light wave. And essentially, this is just, we excite it with light. We excite it with high energy light, which is electromagnetic radiation. And light has magnetic components and electric components, and those will excite the atom via an electrostatic force, a magnetic force, all that good stuff. And when we see if you think like liquid hydrogen, I'm sure probably not many people in this stream have seen actual liquid hydrogen, but we see this continuous phenomena. But essentially what this spectrum is saying is that the energy levels are discrete, right? Like we don't see continuous spectrum. It goes light wave, light wave, light wave, light wave in individual colors. Continuous spectrum would be something like a color gradient. But we don't see a color gradient like you would expect from classical science. And in terms of atomic theory, this essentially says that the atoms are built up of discrete structures. So this is evidence for Dalton's theory. And another thing is the photoelectric effect. This is essentially light with high energy hitting metal. And when it hits metal, it excites the electron in the same way as the last diagram, and the electron will be emitted from the metal at a certain with a certain kinetic energy. And the importance here is that, like, I don't want to go through the math because, frankly, it's awful. But the math here showed something. It showed that the intensity of the light in relation to how much energy the electron had when it was released. Classically, you wouldn't expect intensity to matter just by going through the mathematical motions, but this experiment proved that the intensity did matter. And the hypothesis here to explain that is that light is coming in discrete packets as well, individual photons. And obviously, if you think of like a ball hitting another ball, if you have a sea of balls and you shoot multiple balls at it, the more balls you shoot at it, the more of the original balls are going to move. And in the same sense here, this is saying that light is just this collection of photons, and each individual photon is hitting each individual electron and exciting it. So that's the connection here, because classically we just wouldn't expect that. We wouldn't expect the intensity to matter because we didn't see light as a discrete packet thing. We just saw it as a continuous thing. So summary, classically we only expected frequency to matter, and in terms of modern science, we found out that the intensity and the frequency matter, frequency being proportional to the energy of the light. Another thing, the double slit experiment, the Stern-Gerlach experiment, the black body radiation experiment. These are all further evidence for Dalton's theory. The double slit experiment, you essentially had two slits right next to each other and a wall behind the screen, and you shot electrons into it. And obviously at this point we knew that the electrons were discrete, because you can't shoot something that's not discrete in the sense of this experiment. And it created a sort of bell curve almost on the screen behind on the slits. And that was further evidence, not necessarily for the discrete nature of matter itself, but more so like science was missing something, right? Because there was no classical explanation for that. Like if you shoot a ball with the same velocity and the same angle through a slit, it's just going to hit the back of the screen at the same place every time, ignoring strong gusts of wind, all that good stuff. So this was proof that there was something fundamentally missing, and that was a problem. And the Stern-Gerlach experiment, I don't want to get into the technicality of it, but essentially said the actual movement of electrons was also coming in discrete packets, meaning like if you have a train, or if you really have any object really, let's say the minimum speed is 1 meter per second, the maximum speed is 2 meters per second. It could be in any speed in between there to like the 50th decimal place. But in the sense of what the Stern-Gerlach experiment proved is that the momentum of the electrons that are around the nucleus also came in discrete packets. So it didn't come in a range of values. It came in some integer multiple of some set value. Black body radiation, you see the graph here. Essentially what black body radiation is, a black body is a body that's absorbing all the light that hits it. And we have this literal black body, and we poke a hole in it, and we look at the radiation coming out of it. And what was expected was the red graph you see, that's a parabola. We expected the energy density to be proportional to the square of the frequency of the light. What was actually observed was that big expression right there, the frequency cubed, e to the, all that good stuff. And there was no classical explanation for that. So there's obviously something missing here. What was expected was the energy density of the black body would keep on going up as the frequency of the light went up. But what was actually found was there was some maximum energy density, which puzzles scientists because electromagnetic theory was not enough to describe that. So there needed to be something called a quantum theory. And in summary, classical science just wasn't enough. And the discreteness of nature became more evident because it mathematically explained these anomalies. I've never gone through the math. I'm in a quantum class right now. We're probably never going to get to the math because it's really hard. We went through the mathematical motion of the energy density being proportional to the square of the frequency. I doubt we're going to be able to prove the second thing, what was actually observed in the experiment. But essentially what I can tell you is that the discreteness of nature, if you include the discreteness of the atoms inside the black body, you do get that result. Can I tell you why? So all this led to quantum mechanics. I just put pretty equations on the board. You don't have to worry about what any of those mean. I do, sadly. No, not sadly. I actually really love this stuff. But this is a completely new way to think about science, and it revolutionized electronics, and it's still revolutionizing electronics. There's a push right now in college level engineering degrees, or at least this is what my advisor told me. I'm not an engineer, so I don't know if this is completely true. What he told me is that sooner or later, engineers are going to be required to take quantum mechanics. And this is because the actual electronics that we use to do stuff, they're getting smaller and smaller and smaller. Like if you think someone that rhymes with Iron Man, I'm kidding, I can say his name, Iron Man in Infinity War, like the nanotech, when he pressed the button and his suit just kind of like manifested onto his body, like that's becoming a reality because of quantum mechanics, because we're learning better how to manipulate those little molecular bodies there to create something bigger. Or for example, soon we'll probably be able to get like literal injections of tiny little robots that attack tumors. And then there's a quantum computing race, which essentially, I wrote a paper on this actually over the summer for one of my classes. So I'm not going to go too in detail because I really like talking about this. A classical computer bit can either be 0 or 1. Every string of data is comprised as a combination of 0 and 1s. But a quantum bit, exploiting superposition, can be in a state of both 0 and 1 at the same time. That's not actually right, but I'm oversimplifying here. And this leads to a quantum bit, or a quantum string of bits, being able to store 2 to the n bits of data, rather than a normal bit being able to store, a normal string of bits being able to store n bits of data. So there's literally an exponential increase in the amount of data here. Right now, China's trying to fund research for that, all that good stuff. So this is like really important. And that's what I really want to stress here. I can go on about all the ways this kind of stuff applies. The important thing here is that this matters. This really, really matters. And it's important to know why it matters. I know this is a long way off for like everyone that ever watches this video. But I really do recommend going further in chemistry, just because if you take physical chemistry, you'll learn all about the quantum mechanics behind chemistry, and you'll have the mathematical tools able to properly analyze the quantum systems. And it's super revealing, like really revealing. It's really cool. So done with that spiel. We're going to talk about subatomic particles, and these are essentially the building blocks for everything: electrons, neutrons, protons. And I don't have a diagram here, but essentially what this is you have a nucleus, that's neutrons and protons, which are massive particles at the center of an atom, and electrons not orbiting in a strict sense, but they are definitely around the atom. just sort of chilling, like flying around it, but not in a circle like you think you would, like in terms of like the moon rotating the Earth or the Earth rotating the sun and all that good stuff. But essentially, the original model here was the Bohr model, which was exactly that. It was a nucleus, a charged nucleus, and a charged electron, and the electron was rotating in a circle around the nucleus. And this was an approximation. It was good enough to get, like, we could calculate the radius of a hydrogen atom pretty well for their time. But it's an approximation. And electrons don't contribute to mass. They're often considered massless. They have a mass of 9.11 times 10 to the negative 31st kilograms, a charge of negative 1.60 times 10 to the negative 19th coulombs. And I put the squiggly equal sign there because that's the approximate volume. We never really calculated the volume of an electron. But yeah, so you put that in the chat. That's right, the planetary model of the atom. And the thing here is I put the volume of helium is approximately equal to the volume of an electron times 10 to the 30th. And this is why we consider electrons to be point-like. Like, we act like they don't have any radius at all, because, like, you'd have to have 10 to the 30 electrons to make up for the volume of helium. And helium's already really, really small. So we almost always ignore the size of electrons. And that's very important for atomic trends. I think I do the atomic trends stream next week. So tune into that. Same time, Thursday, 7 EST. But in the same sense, it's very important. Neutrons, they don't contribute to charge, but they do contribute to mass. It's essentially all there is to neutrons. If you want to learn more about neutrons, it's a very big thing in nuclear physics and nuclear chemistry. Sadly, nuclear is not part of the AP curriculum, which I personally very much disagree with, because it's super cool and very useful and almost always taught in a college chemistry class. But if you want to learn more about neutrons, you can, but they're really only relevant because of mass. Protons. Protons contribute to both mass and charge. They have equal but opposite charge to an electron. 1.67 times 10 to the negative 27 kilograms. 1.60 times 10 to the negative 19 coulombs. And protons essentially define what an element is. 1 proton is a hydrogen atom, 2 protons is a helium atom, 92 protons is a uranium atom. And now we have this +1 equals that charge. And that's kind of concerning for people that haven't really learned chemistry before, that like we just kind of assign a number to something. But this is essentially for simplicity purposes, because we never really talk about the units of charge because they're not relevant. Units of charge are relevant in like calculating forces and calculating potential energy, but in terms of chemistry, they're not really important. So we often simplify it to +1. So in this sense, a proton has a +1 charge, an electron has a -1 charge, and a neutron has a plus or minus 0 charge, plus or minus because -0 is +0 are the same thing. So we denote the electron with a E-, sort of like a squared symbol, but with a minus sign. Neutron with an N, it's either N or N0 because it has 0 charge. And then we denote a proton with either P+ or H+. It's H+ because 1 proton is a hydrogen atom, and a hydrogen atom, a neutral hydrogen atom, is just a electron and a proton. But if it's an H+, that means one of the electrons is stripped away. So an H+ is the same thing as a proton, and that's also important in acid-base chemistry, which comes later in the year. But we have a plot twist. So in 1964, there was a proposal that atoms were made of even smaller building blocks called quarks. And in 1968, there was evidence for it experimentally. And these are the most fundamental, most basic structural component of atoms. You cannot split up quarks, or we haven't learned how to split up quarks yet. You can split up atoms via, gluons were also discovered. But in terms of what we're talking about, it's not too important. So yeah, those are the most fundamental building blocks. We haven't learned how, or haven't found out a way to split up protons and neutrons into quarks yet. An up quark has a +2/3 charge, coming from the simplification from the last slide, and a down quark has a -1/3 charge. So I'm going to ask a bit of a challenge question here. which side do you guys think makes up a neutron? As in which side, the left side of the screen or the right side of the screen? Come on, guys, don't be shy. That's right. Yeah, the protons are on the left, and a proton is on the left, and not an electron. That's a neutron. But the neutron is on the right, and the reason for it being, if you add up the quark charges on the right side, they add up to 0, and that's the charge of a neutron. And if you add up the charges on the left side, that's a +1 charge. That's a proton. I hate the cold. All right, so overall structure. Protons plus neutrons form the nucleus at the center of the atom, and the nucleus has mass, has charge, and the electrons travel around the nucleus without mass and without volume. That's honestly a really good question. I don't know if electrons are made out of quarks or not, but if you want to look that up, that'd be great, like right now, because you could tell me that, because that'd be a great thing to know. So electrons travel around the nucleus, and they're bounded by the electric force. But what's the electric force? Coulomb's law, basically the equation for an electric force. Non-technical, opposites attract, like charges repel. Closer charges have more effect on each other, and that's hopefully common knowledge amongst you guys. But let's dive a little deeper into the details. The electric force is KQ1, Q2 over R squared, and electric potential energy is KQ1, Q2 over R. K is just a constant. I put the numerical value there with the units on there. And Q1 is a charge on one charged particle, Q2 is a charge on another charged particle, and R is the distance between their centers of charges. And in the sense of like an atom, we can assume that the radius of each individual thing, like the radius of the nucleus and the radius of the electron, are negligible. So the distance between them is almost identical to the distance between their centers of charges. The center of charge is just literally being the geometric center of the object. And I transform K into a more direct value, just using the simplification of +1 equals 1.60 times 10 to the negative 19 coulombs. And this is essentially saying as charge increases on either charged particle, the potential energy increases, and as distance decreases between charges, potential energy decreases. Now I'm going to make a distinction here. When you're calculating force, you ignore the signs in the charges, but when you calculate the product of the charges and potential energy, you don't ignore it. So like a -1 charge and a +1 charge will produce a negative potential energy. And there's a reason for this. So fundamentally, particles move to decrease their potential energy, right? Like if I drop my phone on the ground right now, which I'm not going to do, even though my room's carpeted, it's moving closer to the Earth to decrease its potential energy because its potential energy is proportional to the distance between the ground and the phone. So it's decreasing its potential energy to 0. And in the sense of potential energy, what you have when you have two positive charges or two negative charges, you'll get a positive value for potential energy. So when you positive value potential energy, how they decrease their value is by moving further apart, right? Because if you have a positive value over R and R is increasing, potential energy is decreasing. However, when one of them is negative, it's in the same sense that the actual value of potential energy, ignoring the sign, is increasing. That's true, but when the charges are oppositely charged, they're becoming more and more negative, which is decreasing their potential energy. So an important note here is you want to know how to calculate this. Don't memorize this formula. I think the potential energy thing used to be on the chem exam, but it's not anymore. But you will have to know how distance and charge affects potential energy and motion of particles, just because it's very important. And it becomes even more important if you take organic chemistry, when you learn about reactions and how acids and bases exchange protons, all that good stuff. So a little bit of relevance here. These equations give you the ability to easily see which network solids, which will be defined in a later stream, require more energy to break. And the example here, I'm going to turn this example over to you guys. Which of the following compounds has a higher boiling point? And boiling point meaning the higher boiling point something has, the more energy that's required to break it apart, because a higher temperature means higher energy. So I'm going to give you some time for you guys to answer that. If you guys want me to go back to the previous slide and show you that equation to find out which one is a higher boiling point, I will. Just give me the word. So I'll give you guys about 20 seconds to do that. Do we count the charges to calculate the equation? Yeah, that's right. Yeah. It's dependent on the product of the charges. Don't have to be shy. No judging here. This is kind of an out of the ballpark question. So I'll go to the next slide then. So the answer is the silicon dioxide. And the reasoning is because if we look back at the original equation, the potential energy, or rather, I'm going to go for the force here. The force, when we calculate the force, we ignore the signs of the charges, right? So the product of the charges, the absolute value of the product of the charges is going to be proportional to the force. So when we go here, we look at the product of the charges. For silicon dioxide, for SiO2, when you look at the charges and we ignore the signs, 4 times 2 is 8, but for the sodium chloride, 1 times 1 is just 1. So if we assume that the distances between the atoms are pretty similar, which you can almost always assume, the actual product of the charges is much greater, right? 1 is 8 and 1 is 1. And this is supported with experimental evidence. The boiling point for silicon dioxide is 2,230 degrees Celsius, and the boiling point for sodium chloride, which is table salt, has a boiling point of 1,465 degrees Celsius. Yeah, that's exactly right. Yeah. No, that's completely right there. Good job, bud. Yeah, so more force, they hold on to them tighter. Yeah. And just for comparison, the temperature of the sun's surface is 5,505 degrees Celsius. Don't ask me where that calculation came from. I'm not an astronomer. I don't know where that came from. But, you know, in the same sense, this is how you would determine that kind of question. So we ignore negative signs in this context because the sign of potential energy will always be negative. So in this case, 4 times 2 is 8, 1 times 1 is 1. But when we're comparing two values and they're both negative, the negative sign doesn't matter, right? Because we're comparing two negative numbers. So the negative sign really doesn't matter when we're comparing them. Another way to think about it is, I mentioned in the previous slide that the lower potential energy something has, the more stable it is, or the rather particles move to lower their potential energy. So the most stable state is the lowest energy state. And in this case, lowest energy, it's kind of confusing because the concepts go like backwards and forwards, but lowest energy being the most negative energy. And when you have a compound like this where there's a negative charge and a positive charge, it'll always be negative. So you look at the thing that has the most negative charge, and the most negative charge, that silicon dioxide would have about 8 times the negative potential energy that sodium chloride does. And in the same sense here, that fancy little fishy looking character just means proportional to, and the K under means it's proportional by that constant. But you don't have to worry about K because you're not calculating anything. So 8 is greater than 1, so the silicon dioxide bonds are stronger than the sodium chloride bonds for the same reason that you mentioned in the chat. The protons in the silicon dioxide would hang on to the electrons more tighter, or more tightly rather. And that means that the silicon dioxide bonds require more energy to break, which means that the silicon dioxide has a higher boiling point. If you don't know what silicon dioxide is, that's sand. So we're looking at the boiling point of sand versus salt. And turns out sand has a greater boiling point. So if you were trying to boil sand this weekend, sorry to ruin your weekend plans. Next thing, isotopes, hyphen notation, nuclides, and mass number. So as I mentioned before, protons determine what element an atom is. Neutrons give it a varying mass. And an element with a certain number of neutrons is called an isotope. So we could have let's say a hydrogen with 1 proton and 1 neutron and 1 electron. This is the most common form of hydrogen. We can add a neutron in there, and it's still hydrogen, right? But it has 2 neutrons, and it has 2 neutrons, 1 proton, and 1 electron. It doesn't affect the charge because neutrons are chargeless. I think this is called, I know if you take 2 of these and form a water, it's called deuterium, I think. But for some reason, I think it was some channel that like tasted it and they said it was sweet, which really confused me because it's not chemically different, so it shouldn't taste any different, but whatever. So you can have different number of neutrons in an element, but as long as each thing has the same number of protons consistently, it's the same element. And a certain isotope of an element is called a nuclide. So for example, the hydrogen with 1 nuclear or with 1 neutron, the hydrogen with 2 neutrons, they're not the same nuclide, even though they're the same element. And each element has a range of isotopes, and those isotopes have a different stability. Stability meaning how long it will last in nature. And if an element has an unstable isotope, it will decay, and this is how nuclear reactions happen. So again, this is a really important thing, especially in American culture and our obsession with the nukes and nuclear energy. Well, much less nuclear energy, but that's a different topic. So most helium, which is 2 protons, have 2 neutrons, but some of helium atoms only have 1 neutron. A very low percentage, as you can see, 0.0002% of helium atoms have only 1 neutron. So the logical conclusion here is any atom can have any number of neutrons. However, the half-life, that's what T1/2 means, of a helium with 3 neutrons is like very low. And the half-life for helium with 4 neutrons is also really low, much greater than the first half-life, but still very low. Like you wouldn't be able to see it with your eye unless you have a crazy reaction time. So the crazier number of neutrons lead to instability, which is the reason radiation is a natural process. And one thing that I'm going to bring up here because I forgot to, if you're wondering why protons stay together in a nucleus, because like electric force, they should repel, like charges repel. And that's true on a macroscopic scale. However, when they get really, really close together, there's something else called the nuclear force, and that nuclear force gets really, really, really strong at close distances. So these protons they'll obviously, they will repel each other. If they didn't repel each other, then literally everything would be attracting in our world. But once they reach that certain distance threshold, I really wish I had a potential energy diagram to show you guys this. But once they reach that certain threshold, they'll start attracting each other. And the same goes with neutrons. Neutrons also experience the nuclear force. So isotopes are notated as such in the isotopic form. There's element A with mass number n plus p, which is m in the top. And p is the number of protons. And there's also the hyphenated form, which is A-M, which is just the element dash the mass number. So for example, a helium with 3 neutrons would be helium-5 because helium has 2 protons, and you add the number of protons with the number of neutrons, and that forms the mass number. So helium-5, or that helium with the 2 down here and the 5 up here. Same goes with the helium with 4 neutrons. 4 neutrons plus 2 protons, same number of protons because it's still the same element, would be helium-6. And that would have the 6th script up there. I don't formally know what it's called. I know subscript and superscript are on the right. I don't know what it's formally called for the left side, but that's how to do it. So problems. Convert the following into hyphenated form. Uranium, which has 92 protons, which is 143 neutrons. And a bit of a challenge, given that this atom above has a neutral electric charge, how many electrons does it have? So again, I'll give you about 45 seconds to solve that. I'll give you guys 45 seconds. So go ahead and try and work that out. Again, don't be shy with answering the questions. Even if you do get it wrong, it's a learning experience. So go ahead. I'm going to see who's actually in the stream because okay, so there's 3 people in the stream: Elizabeth, Adam, and Caitlin. And yeah. Yeah, that's why no one's answering, because no one's here. Sadly, chem is a really, it's like a fear-mongering subject. Like everyone's like, oh no. Yeah, that's right. That's 238 actually. I can't add. Or maybe I can add and add correctly in the slides, which is a problem. And in the same sense, number of protons, yeah, 92 electrons, you're right. So whenever an isotope has charge, it's denoted by a superscript. So for example, chlorine with 17 protons, with 18 neutrons and 19 electrons, that would have a -2 charge, a mass number of 35, and a elemental number, which is just the number of protons of 17. So that's what that would look like. You know, occasionally two atoms will be bonded together, like hydrogen gas exists as two hydrogens bonded together, and the subscript will be a 2. So yeah, we're going to move on to something a little more complicated, which is mass spectroscopy and average atomic mass. The first one's complicated, the second one isn't. So mass spectroscopy is a lab technique that measures mass per charge. And if we have mass per charge and we know the charge of the atom, we can measure the mass. Obviously, mass per charge times charge equals mass. And essentially, what this process is we have something shooting a big sample of an element into a beam. And once it goes inside a magnetic field, those beams will separate based off of how much charge they have, because charge is proportional to the magnetic force. So therefore, it'll be pulled more or less depending on how much charge it has. And from there, it goes into these reservoirs, and we can tell just by statistical analysis how much percent of, or how much of an atom or sample on Earth by percentage will be a certain isotope. So if you take in physics, that's the derivation right there for the radius of the object moving in a circle based off the strong magnetic field. And this says the radius is proportional to the mass per charge. If you've never taken physics, just trust me, dude. But you really don't need to take physics to understand this. So the higher mass per charge means a higher radius, which means that it'll diverge further from the path. So yeah, so we essentially look at the mass per charge, and we can see how much it diverges away from the original path. And then we can see, based on statistical analysis, if the sample is big enough, we're able to extrapolate the data from that sample and do things with it, which is nice. And from here, we can form a mass spectrum. And this says you can see how much of a sample has different masses to create a spectrum. So this is a chlorine spectrum. Chlorine spectrum says that 75% of chlorine atoms have a mass number of 35, and 25% of chlorine atoms have a mass number of 37. And from here, we can calculate the average atomic mass. The average atomic mass is just the sum of the atomic, or the mass number, or the proportion. Yeah, that's right. Yeah, that's a really good analogy, actually. And from there, we can sum that up, the proportion times the atomic mass of each isotope, and we can see the average atomic mass. If you have a periodic table on you, there's a number below the element. That's the average atomic mass, and that's how we calculate the average atomic mass for things. Now, there's some elements that simply aren't, average molar mass, that there's just some that aren't stable enough to perform this experiment on. In which case, we don't really know. Instead, those numbers, they're in parentheses on the periodic table. It's simply on the periodic table the most stable isotope of the element, and we can sort of extrapolate from that idea, like logically extrapolate from that idea. The most stable isotope is the most common isotope, but we don't really know. So I'm a little early, but I did go through that pretty quickly. So we're gonna have an open discussion now. You can ask any questions. Do you have any questions that I could answer that are going to be on your test that I didn't really talk about in the slides? Because A, it's my job to make sure you're prepared, and B, I also just love it. So. What does PES stand for? Because it's definitely familiar. It's just I haven't taken Gen Chem. Photoelectron spectroscopy. Yeah, I mean it's a I don't remember, but I have to keep on drinking this because I'm really sick. But yeah, I mean, from what that sounds like is you use light to see how many electrons are in an atom. Photo meaning light, electron. Electron meaning obviously electrons shine out of the electron. And you create a spectrum, spectroscopy, to see, how many electrons. But I'm not sure. I think that might be just this same spectroscopy technique, but using light. Yeah, I mean that would make sense because like the light's really thin, and you can analyze the electron clouds and the orbitals and the size of the orbitals based off that. Yeah. Well, if my like the dissection of the word is right, then the light would provide a magnetic field, just an albeit small one, but a small one would be enough to affect an electron. I mean, if you give me like a question regarding like the subject, like an actual like question that was like put on like a review by your teacher or something, then yeah, I could definitely answer it. But like, I only know spectroscopy because like we're about to do it in my physics lab. So, but yeah, I mean, if you have like a direct question from your review, I could definitely answer it, or like a more general concept. Because a lot of like this stuff like isn't really like photoelectron spectroscopy. Like you're not going to be asked like, what does a spectrometer do, or maybe you will be, but not like how does a spectrometer function? So like I just simply don't know because it's not relevant for the exam. But if like obviously a question regarding it will be relevant. So. Okay, so this is actually next week's stream, but I can talk about it now. Essentially, you can you can compare sizes of the atom and the periodic table at the very bottom with francium. Francium is the largest atom and the largest radius as such, and therefore the electron or the force between the electron and the nucleus is weaker for bigger atoms. So that would have a smaller ionization energy than something like hydrogen, because hydrogen's a really small atom. So you'd have to look at the sizes of the atom. Yeah. And second ionization energy is just the same case. And the trend gets a little more complicated when you're including charge and all that good stuff. I can't really explain why that trend works, why francium is the largest atom, without drawing a picture out. That will definitely be on the next stream, though. That there will be a picture for you to, actually visualize it. And it's the same thing with like knowing a lot of fundamentals about your subject. The fundamentals for like why a francium atom is like larger than like a fluorine atom. You're not going to know like, oh yeah, here's how the electric force interacts with the between the electrons and adjacent electrons and the electron in the nucleus. But I still go over it just because it's important to know the fundamentals, because essentially you're just memorizing trends, and eventually your brain's not going to have enough pure data to memorize that stuff. So it's important to more or less code the process in your brain, because you can keep more code in your brain than pure like methodology, in my opinion. But yeah, if that's it, then the stream's done. I hope you learned a thing or two. Again, follow Think 501 social media if you want to get alerted for all the streams. There's a lot of subjects on 501. There's not just sciences. Actually, it's mostly not sciences. That's why these science streams have no viewers. But yeah, you'll get notified through Instagram. Again, next week we'll be doing next stream is next Thursday at 7. I try to make every single chemistry stream that I do Thursday at 7 EST, just because that's the best time for me, because I'm busy. I'm a busy college student. I'm a physics major. We have too much work to do. So I try to keep it at that time. I try to keep it consistent. So yeah, my next trend will be on periodic table trends and all that good stuff. You know, how to determine whether an atom will have more or less energy required to pull an electron off of it. That was the first or second ionization energy. First ionization energy being pulling the first electron away, second one being pulling the second electron after that. We'll be talking about atomic size and, you know, all that good stuff. Yeah. You're free to eat dinner, dude. Like, I have no more material. See you later, dude. Hope to see you on Thursday. Last minute questions, anybody?